This video, in the lecture on cell balancing, addresses heat dissipation in the circuits implementing balancing. Let's do some electrical engineering. Here's a typical balancing circuit with resistors and MOSFET switches. To balance a given cell, we close the corresponding switch and a current flows, discharging a selected cell. The switches may be implemented in a single ASIC, which stands for Application-Specific Integrated Circuit, or colloquially a chip. Another general term for such a chip is AFE, or analog front end. You can find chips that integrate switches to balance 6 or 12 or 14 or 18 series cells. The balancing resistors are often implemented external to the chip, on a PCB or printed circuit board. These balancing resistors may dissipate more energy than anything else on the PCB, so in some designs, care must be taken with thermal management of the dissipated energy. For example, say we want to design for up to 15 milliamps of imbalance and to spend no more than 2 hours per day balancing. We need a 180 milliamp balance current. With the circuit as drawn on the left, each of the resistors must dissipate about 1/3 of a watt. Looking at popular surface mount resistor ratings, note that a fairly large resistor is needed to dissipate that much power. Unfortunately, larger components tend to be a reliability headache. Since a component and the PCB have different coefficients of thermal expansion, as a board is thermally cycled over its life, every thermal cycle puts stress on the solder joints, and those stresses are larger in the case of larger components. In practice, then, the designer must strike a balance between the trade-offs. One solution is to use a smaller balancing current, and in the small fraction of units that show a worst-case self-discharge, balancing may need to run a larger fraction of each day. Another solution is careful thermal design and implementing each balancing resistor as several series resistors. A smaller balancing current can meet our constraints if we balance a larger fraction of the time. For example, if we decide that balancing 50% of each day is okay, then we can reduce the balancing current to 30 milliamps, requiring only 60 milliwatts of heat dissipation in each balancing resistor. An 0805 size surface mount resistor is rated to handle that. Another trick is to implement each balancing resistor as several series resistors. The dissipated power now meets the 0805 resistor specification. Calculating the total heat dissipated on the board, however, if we consider balancing every other channel of a 12-channel chip, we're looking at 4.3 watts, which is a lot to dissipate on a small PCB. Remember that this PCB is likely inside the battery pack, which is to say, inside an unventilated metal box. Dissipating this much power requires careful thermomechanical design. Let's roughly estimate how hot the PCB might get with 4.3 watts of dissipation. For the sake of example, consider the LTC 6813 evaluation kit. The balancing resistors are here. The whole board is about 100 millimeters across. Let's assume our layout incorporates a large heat-spreading ground plane such that those 4.3 watts are dissipated over an area of 10 by 10 centimeters. Zoom out a bit and consider how the board is situated. Imagine it's co-located with the cells inside a sealed battery housing. We'll calculate the heat transfer from the PCB to ambient across a distance d. You may have seen the heat transfer equation. I think it's a very intuitive equation. Q is heat, and Q over time is power in watts. Kappa is thermal conductivity. Power and kappa being proportional makes sense. We'll see more heat transfer through a material with high thermal conductivity. The thermal conductivity of air is 0.028 watts per meter per Kelvin. A in the heat transfer equation is area. This also makes sense. You can expect more heat transfer across a large area. Delta T is the temperature gradient across the gap. Again, intuitive. A large temperature difference means more heat transfer. If you touch a hot stove, your finger will get more heated than if you touch a warm cup of tea. Little d in the denominator is the distance across which the heat moves, and as the gap increases, the heat transfer decreases. Think of an insulated bottle. Thick walls insulate well, meaning low heat transfer with a large d. Now, we can rearrange the terms to solve for delta T and plug in the values we've collected. I've assumed 1 centimeter for D. In the case of the board shown, the connector thickness would limit the minimal possible air gap. Notice the result, 153 degrees. This is not a math error. 4.3 watts is a lot of energy to dissipate on a PCB. That evaluation kit isn't designed to handle the balancing current advertised on the front page of the LTC 6813 datasheet. So what can we do? One option is to reduce the watts. Consider reducing the balancing current to 30 milliamps. With 6 channels balancing concurrently, that reduces the power to 7/10 of a watt. That, in turn, reduces the temperature gradient to 25 degrees. With a 45 degrees centigrade ambient temperature, which is about the max okay for lithium-ion cells, a 25C gradient results in a 70 degrees centigrade board temperature, which is quite reasonable. This is compatible with good reliability targets. Another option is to dissipate the heat better. Consider an aluminum heat sink to couple the PCB to the cells and calculate the heat transfer from the 10 by 10 centimeter PCB across a 2 millimeter thick aluminum heat sink. The thermal conductivity of aluminum is about 9,000 times larger than that of air. When we update the values of D and kappa, even with 4.3 watts on the PCB, the temperature gradient is negligible. Now, this is an optimistic approximation. We've ignored the thermal conductivity of the resistors to the PCB and dissipation across the PCB. 4 millidegrees is not a realistic value. The point of this slide is that a heat sink takes us out of the realm of impracticality. As a side note, this design solution requires some consideration of the impact of heating the cells. In particular, warmer cells age faster, and this arrangement results in locally heating the cells adjacent to the PCB. We might expect consequently unequal cell aging within the pack. In summary, high balancing currents require careful thermomechanical design and validation of the PCB. Component overheating is a concern, which we discussed with regards to the balancing resistors. The thermal dissipation of the BMS chip itself also can be a concern. Additionally, operation at high temperature reduces component reliability and lifetime. Lower balancing currents are easier to implement. Now that we reviewed PCB thermal considerations, let's take a look at some BMS chips available on the public market, what balancing currents they support, and corresponding thermal implications. Let's look at 3 BMS chip datasheets and compare what balancing currents are advertised for chips on the market today. The first thing I notice is that the balancing current advertised on the first page of the datasheet is quite similar for these 3 chips. The second thing I look at is the resistance of the on-chip switches that control balancing. Given that they are nominally designed to conduct very similar currents, we might expect the switches to have similar resistance. However, one of these chips has twice the resistance of the other 2. And since power is I squared R, doubling the resistance may double the on-chip heat dissipation. Last, let's look at some additional comments in the datasheets. The LTC 6813 allows 200 milliamps of balancing current, but only 80 milliamps if the die temperature is over 95C. The resistance of a MOSFET increases with temperature. The hotter the transistor gets, the more heat it dissipates. It's a bit of positive feedback. I expect this relationship to be true for all silicon chips, whether they include a note to this effect or not. For the BQ79616, note that 75C assumed in the note is quite similar to the 70C board temperature we estimated and said was okay a few slides back. Oftentimes, mature engineering solutions from multiple vendors look similar. I told you 70C is okay for a PCB. Texas Instruments assumes 75C for ambient, and for a chip with an exposed pad, the PCB and ambient are nearly the same. Analog Devices list the die temperature only slightly higher. This suggests we're all 3 roughly in agreement on this scenario being relevant. We saw in the previous slides that achieving a roughly 200 milliamp current can be challenging at the board level. Assuming we've addressed board level heat sinking well, how does it look for the chip? This circuit shows how a typical balancing circuit is implemented. To model the on-chip heat dissipation, we can replace the MOSFET switch with a resistor with value RDS on. RDS on stands for source drain on resistance. Let's calculate the heat dissipation for the 3 chips. Since most chips cannot balance adjacent channels, for a 12-channel chip, the worst-case thermal situation is with 6 channels balancing. In that case, the power dissipated on the chip is 6 times I squared times RDS on. We can repeat that calculation for the 3 chips with their 3 different RDS on values. I used 200 milliamps for the LTC6813 and TLE9012, and 240 milliamps for the BQ79616, since those are the values promoted in the respective datasheets. The LTC6813 is an 18-channel chip, so perhaps we should assume 9 channels balancing. With the maximum amount of balancing allowed by the datasheet, we can expect each chip to dissipate 1.3 watts to 3.6 watts. Next, let's calculate how hot those chips will get. We'll start with the relevant thermal specifications for those 3 chips. All 3 of these chips have an exposed pad, which is a metal pad on the bottom of the chip. Like the pins, the exposed pad is soldered to the printed circuit board. The exposed pad and solder provide a path for heat transfer from the chip to the board. The board should be laid out with a large ground plane to then conduct the heat laterally. Each manufacturer also quantifies the heat transfer characteristics of their chips. RTHJA is the thermal resistance from junction to ambient, with the chip mounted on a standardized test board in a still air test cube 305 millimeters on a side. RTHJC is the thermal resistance from junction to case, which refers to the heat transfer from the silicon die to the outside of the plastic case or to the exposed thermal pad. As you can see from these numbers, the exposed pad substantially increases heat transfer. With the power dissipation we calculated 2 slides ago and the thermal resistance from the previous slide, we can calculate each chip's internal temperature increase due to balancing. Lastly, we can ask what die temperature we can expect with 45 degrees C ambient, which is about the hottest that a properly managed lithium-ion battery should be. One of these is rather high. This chip can be purchased in 2 variants, and expecting a 106 degrees C temperature, we must order the one with the wider temperature operating range. We also need to consider lifetime and reliability targets. Even the 80 degrees C operating temperature can be a concern for the reliability of products with a long lifetime. But an 80 C peak temperature is probably okay as an intermittent state, and balancing at such high currents likely would be intermittent. One takeaway is that sensing the die and board temperatures during balancing may be worthwhile. Many BMS chips on the market incorporate die temperature sensors and circuits to support thermistors external to the chip. Let's repeat the calculations with RTHJC, that is, accounting for the exposed pad and assuming excellent heat sinking from the exposed pad. The temperature deltas are much smaller, resulting in very reasonable die temperatures with 45 degrees C ambient. This math is correct if the PCB to which the exposed pad is soldered remains at 45 degrees. In practice, an exposed pad to a PCB ground plane is a less ideal scenario than this situation captures. This math neglects the limited thermal conductivity through the PCB and then dissipation from the PCB to ambient. The takeaway is that PCB layout matters to thermal design. With high balancing currents, it may be worthwhile to pay for thicker metals in the PCB, and a heat sink on the PCB may be worth considering. The actual die temperature is likely to fall somewhere between what we calculated with RTHJA and RTHJC. Let's summarize what we've learned about the thermal design of balancing circuits. Balancing resistors need to be physically sized to dissipate the expected amount of heat or power. The roughly 200 milliamp balancing currents promoted in many BMS chip datasets require careful thermal design to ensure sensible PCB temperatures. BMS chips balancing at about 200 milliamps often feature an exposed pad to provide a heat transfer pathway from the silicon die to the PCB ground plane. Consider both typical operating temperature range and long-term reliability. This is the end of the video on thermal considerations around the cell balancing circuit. If you liked what you saw, please help this course get seen. Share it with a colleague, share it with a customer, share it with a favorite college professor, and then continue the cell balancing lecture in the next video.